Myself Laksha from MSc Chemistry first year. Today I am making a video from Physical Chemistry Unit 2nd Thermodynamics. Thermodynamics, it is a branch of thermodynamics which deals with the heat change and flow of physical process. The first law of thermodynamics gives relationship between heat and work. Second law of thermodynamics deals with direction of flow of heat and feasibility of the process. Third law places a restrictions on value of entropy of a crystalline solid. System. The part of universe in which heat change occurs is known as a system. Surrounding. The remaining part of universe which change heat occurs is known as surrounding. Boundary. Anything which separates system and surrounding. Closed system. A system which can exchange only energy not mass with surrounding. Isolated system. System in which neither the energy nor the mass can be exchanged with surrounding. Homogeneous system. If it is a completely uniform throughout, such a system has only one phase. Heterogeneous system. When it is not uniform throughout, such a system has two or more phases. Microscopic system and macroscopic properties. A system containing large number of particles is called microscopic system. The properties of system which arise from the bulk behavior of the matter are called macroscopic properties. It can be divided into two parts, extensive and intensive. Extensive property of a system which can depend upon the quantity of system present in the system are called extensive properties. Calculation of work function for two state of system. If A1 is equal to ut minus u1 minus ts1 and a2 is equal to u2 minus ts2, subtract first and second. A2 minus a1 is equal to u2 minus ts2 minus u1 plus ts2. Del A is equal to del u minus t into s2 minus s1. Del A is equal to del u minus t del s. We know that del s is equal to del q by t. T del s is equal to del q. Del A is equal to del u minus del q. According to first law of thermodynamics, F is equal to q plus w. Del u is equal to q plus w. Del q is equal to del u plus w. Put values of del q is in equation 5th. Del A is equal to del u minus w. Del A is equal to minus w. W represented work done by system. So del A is equal to minus w. Del A is equal to minus p del w. W maximum is equal to minus del A. Calculation of Gibbs free energy. G is equal to H minus Ts. G1 is equal to H1 minus Ts1. G2 is equal to H2 minus Ts2. G2 minus G1 is equal to H2 minus H1 minus T into S2 minus S1. Del G is equal to del H minus T del S. We know that del H is equal to del U plus P del V. E is equal to del Q plus P del V. Del G is equal to del U plus P del V minus T del S. Del G is equal to del A plus P del V. Del G is equal to minus W plus P del W. Del G is equal to minus W minus P del V. At constant volume, del V is equal to 0. Del G is equal to minus W. And del G is equal to minus W reversible. Entropy. En energy. Trop change. It was introduced by R.J.E. Celsius. It is the measure of energy, change of energy. It is also a measure of unavailable energy denoted by S. It is given as S is equal to Q by T, where del S is equal to del Q by T. The efficiency of a Carnot cycle is entropy. En energy trop matlab change. It was introduced by R.J.E. Celsius. It is the measure of change of energy. It is also a measure of unavailable energy denoted by S. It is given as S is equal to Q by T. Del S is equal to del Q by T. Efficiency of Carnot cycle is efficiency is equal to T2 minus T1 by T2 is equal to Q2 minus Q1 by Q2. 1 minus Q1 by Q2 is equal to 1 minus T1 by T2. Q1 by Q2 is equal to T1 by T2. Q2 by T2 minus Q1 by T1 is equal to 0. Del Q by del T is equal to constant, that is Q by T is equal to constant. First law of thermodynamics, it is also called as law of conservation of energy. According to first law of thermodynamics, energy can neither be created nor be destroyed. It can convert from one form to another. That is impossible to construct a machine which will work continuously without consuming energy. That is, there is an exact equivalence between heat and work done. Mathematical form of first law of thermodynamics. Initial Q plus W is equal to final state. E2 is equal to E1 plus Q plus W. E2 minus E1 is equal to Q plus W. Q is equal to del E plus P del V at constant volume. QV is equal to del E at constant pressure. QP is equal to del P. Q is equal to heat, E is energy, W is work done, del E is equal to Q plus P del V, del E is equal to Q plus W. Limitation of first law of thermodynamics. It does not tell about spontaneity of a process, that is whether a process is spontaneous or not. It does not tell about direction of reversible reaction. Zeroth law of thermodynamics. When two bodies are separately in thermal equilibrium with third body, then the two bodies are in thermal equilibrium with each other. For example, suppose we have the three systems ABC are in a constant so that the properties of both the system change and finally the thermal equilibrium is attained. C is constant with B. Also the again thermal equilibrium is attained. If this is so, then A and B should also be in thermal equilibrium, that is ABC should be in same temperature. Three systems are in thermal equilibrium. Second law of thermodynamics. To overcome the limitation of first law of thermodynamics, this law was introduced. According to second law of thermodynamics, heat can't spontaneously pass from a colder to a warmer body, or entropy of universe is continuously increasing. Kelvin's statement: it is impossible to convert heat completely into work without leaving some effects in the system or surrounding. Kelvin-Planck's statement: it is impossible to construct a machine which operates slowly by removal of heat from thermal reserve. Clausius' statement: it is impossible to construct a machine that is able to transfer heat by cyclic process from colder to hotter body without use of an external energy. All spontaneous processes are thermodynamically irreversible. Entropy of the universe is continuously increasing. Energy change from reversible process. Let a system absorb heat at temperature T, S system बराबर है Q reversible by T. Then simultaneously surrounding lose heat reversibly. Surrounding is equal to minus Q reversible by T. Total change in entropy from universe is equal to del S system plus del S surrounding is equal to Q by T minus Q by T is equal to 0. Net entropy for a reversible process is 0. Entropy change for irreversible process. Let a system at temperature T2 which is given by del S system is equal to Q by T2 irreversible. An increase in entropy of surrounding is given as del S surrounding is equal to Q by irreversible by T1. Net entropy change del S T is equal to minus Q irreversible by T2 plus Q irreversible by T1. Q into 1 by T1 minus 1 by T2 is equal to Q into T2 minus T1 by T1 T2. Hence entropy increase in an irreversible process. Physical significance of entropy. It tells us feasibility, it tells us the extent of disorder, it measures the probability. Entropy for fusion is equal to del S fusion is equal to del H by T fusion. T fusion is that temperature at which ice starts to liquid change is known as fusion temperature. Variation of free energy with temperature and pressure. Gibbs free energy G is equal to H minus Ts. Equation first. Enthalpy H is equal to E plus PV. Equation second. Put second in first. We get G is equal to E plus PV minus Ts. Tg is equal to D plus PdV minus Ts plus VdP minus SdT. According to first law of thermodynamics, E is equal to Q plus W. dQ is equal to E plus W. dQ is equal to E plus PdV. TdS is equal to D plus PdV. dG is equal to VdP minus SdT. At constant pressure, dGT is equal to VdPT. dG by dP at constant temperature is equal to V. By using relation dGT is equal to VdP for ideal gas, PV is equal to nRT, V is equal to nRT by P, dG is equal to nRT P dP. Integrate dG is equal to nRT integrate dP by dV. G2 minus G1 is equal to nRT ln of P2 minus ln of P1. Del G is equal to nRT ln of P2 by P1. Boyle's law P1 V1 is equal to P2 V2. V1 by V2 is equal to P2 by P1. Del G nRT ln of V1 by V2. Relation between standard free energy change del G node and equilibrium constant K. Del G node is equal to minus RT ln of K. Variation of entropy for ideal gas temperature and volume. According to first law of thermodynamics, E is equal to Q plus W. Del E is equal to Q plus W is equal to Q plus P del V. dQ is equal to D plus Kp dV. Equation first. Divide equation first by T1 we get dQ by T is equal to D by T plus P dV by T. ds is equal to dE by T plus P dV by T. Equation second, let E is the function of temperature and volume. E is equal to F into TV. D is equal to D by dt V dt plus dE by dV T dV. Equation 3. Put equation 3 in equation second, we get ds is equal to d by dt dt by T plus D into dE by dV dV by dt plus P dV by T. By using Joule-Thomson's law, dE1 by dV is equal to 0. ds is equal to dE by dt V dt by T plus P dV by T. Equation 4th. Now PV is equal to RT. P is equal to RT by V. Equation 5. Put values of P in equation 4. We get ds is equal to 1 by T into dE1 by dt into dt plus plus R by V dV. ds is equal to 1 by T CV dt plus R dV by V. ds integrate s1 to s2 is equal to cv integrate t1 to t2 dt by t plus r integrate dv by dt from v1 to v2. s2 minus s1 is equal to cv ln of t2 minus ln of t1 plus r ln of v2 minus ln of v1. Del s is equal to cv ln t2 by t1 plus kr ln v2 by v1. Equation 6. Entropy change for an ideal gas with T and P. We have PV by T is equal to nR. P1 V1 by T1 is equal to P2 V2 by T2 is equal to V2 by V1 is equal to P1 T2 by P2 T1. Equation 7. Del S is equal to CV ln of T2 by T1 plus R ln of P1 T2 by P2 T1. CV ln T2 by T1 plus R ln P1 by P2 plus R ln T2 by T1. Del S is equal to Cp ln of T2 by T1 plus R ln of P1 by P2. Phase rule. Phase rule is given by J.W. Gibbs in 1876 and thus is known as Gibbs phase rule. For a heterogeneous system in equilibrium at a definite temperature and pressure, the number of degree of freedom is greater than the difference in the number of components and the number of phases by 2, providing the equilibrium is not influenced by external effects such as gravity, magnetic forces, surface tension, etc. F is equal to C minus P plus 2. 2 is including in equation 2 accounts to the fact that the two intensive variables T and P must be specified to describe the state of equilibrium. It states that degree of freedom components phase of a system are related with each other in such a way component phase can be greater than degree of freedom phase. A phase is a homogeneous which is separated from other parts of a system by well-defined boundaries. Component. The smallest independent part of a system which tells us about phase. Example H2O sugar solution. Degree of freedom. The variable that tells us about number of phase and component. It is defined by F. Types of equilibrium. To equilibrium if the same state can be occurs from either the direction. Stable equilibrium if the same state can be occurs from only one direction by a careful change of condition. Example H2O liquid. Unstable equilibrium if the same state not be attained from either direction. Derivation of phase rule. Consider a heterogeneous system consisting of components C1, C2 to Cc distributed among phase P1, P2 to Pp. Let us mu I can be the number of chemical reactions. Distribution of C component in phase. Independent concentration variable for one phase in respect to C component C1. Independent concentration variable for phase P in respect to C component P into C minus 1. Total number of independent variable P into C minus 1 plus 2. Here 2 stands for temperature and pressure. To find number of equation of equilibrium for one component mu 1A equilibrium U1B equilibrium U1N. For C component UCA equilibrium UCB to UCN. For each component the relation for phase P minus 1 for component C. Relation for phase P C into P minus 1. Total independent equations R is equal to C into P minus 1. Degree of freedom F is equal to total number of independent variable S minus total number of independent equation. RF is equal to P into C minus 1 plus 2 minus C into P minus 1. F is equal to minus P plus C plus 2 is equal to C minus P plus 2, which is called Gibbs phase rule. Phase diagram. It is a graphical representation given the conditions of temperature, pressure under which the various phases are capable of stable existence and transforms into various phases. Hence, the relation between the solid, liquid, and gaseous states of a given substance as a function of temperature, pressure can be summarized on a single graph. The diagrams so obtained giving the condition equilibrium between various phases of a system are called phase diagram. Lead silver system is an Two component systems consisting of two component lead and silver. The various phases possible: solid lead, solid silver, solution of lead and silver in the molten states. They are completely miscible. Vapor. Since small changes of pressures have negligible effect on equilibrium existing between lead and silver in solid states or in molten states, so we can use the reduced phase rule equation f dash is equal to c minus p plus 1. According to this equation, f dash is equal to 0, c is equal to 2, 0 is equal to c minus p plus 1, p is equal to 3, then maximum number of phases can be coexist would be 3. The phase diagram of lead silver system is shown in the figure. The diagram is drawn taking the temperature composition along the axis. The equilibrium diagram consists of two curves OA and OB intersecting at point A. O. Curve OA is represented the freezing point curves of silver to which the small quantities of lead are added. The point A indicates the melting point of pure silvers and separation of silver occurs till the point O is reached. At the point no more separation is possible and melting point of silver does not fall. This point is O is called epileptic points. The system is univariant, that is f dash is equal to c minus p plus 1, which is equal to 1. Curve BO it represents freezing points curve of lead to which small amount of silver are added. The point B represents melting point of pure lead. At point O no more separation is possible. Separation of lead occurs till the point O reaches. The system is univariant, f dash is equal to 1. Eutectic point O, this is the point where two curves OABO met, at which point solid lead, solid silvers are in equilibrium, that is, three phases are present. Therefore, there are no degree of freedom according to reduced phase rule. F dash is equal to 0. The point O represents the lowest possible temperature below which a liquid phase can't exist. Such a liquid mixture of two component Ag and lead which has lowest freezing points mixture is called eutectic mixture. The temperature corresponding to the eutectic point O is called eutectic temperature. Clausius-Clapeyron equation. It was initially proposed by a German physicist Rudolf Clausius in 1834. Derivation: consider a system at equilibrium. The free energy change for ongoing process is 0. We know that variation of free energy with temperature and pressure can be formulated by following differential equation. dc is equal to vdp minus sdt for typical single constituent equilibria. Phase 1 equilibria. Phase 2, where phase 1 can be solid, liquid, gas. Phase 2 can be liquid or vapor depending upon the nature of transitions, whether it is melting, vaporization or sublimation respectively. Now consider a system at pressure P and temperature T and the free energy of phase T. Phase 2 of the systems are G1 and G2. If we change temperature from T to T plus dt, pressure P to P plus Tp, the free energy change in phase 1 and second will be dg1 and dg2. dg1 is equal to v1 dp minus s1 dt. dg2 is equal to v2 dp minus s2 dt, where v1 and s1 represent molar volume and entropy of phase 1, while v2 and s2 represent molar volume and entropy of phase 2. If the phase 1 and phase 2 are in equilibrium, del G is equal to 0, G2 minus G1 is equal to 0. Now G1, G2 are simply the free energy of phase 1 and phase 2 at temperature T and pressure P. We can say the same must also be true at temperature T plus Dt and pressure P plus Tp. G2 plus D, G2 minus G1 plus D, G2 is equal to 0, G2 minus G1 plus D, G2 minus D, G1 is equal to 0. Since G2 minus G1 is equal to 0 from equation 3, above equation will be v2 dp minus s2 dt is equal to v1 dp minus s1 dt. v2 dp minus v1 dp is equal to s2 dt minus s1 dt. Del v into dp is equal to del s into dt. dp by dt is equal to del s by del v. Now if the del h is the latent heat of phase transformation occurring at temperature, the entropy change del s is equal to del h by t. After using the value of del s from equation 5th and 4th, we get dp by dt is equal to del h by t del v. Now if phase 1 is called Vahil, phase 2 is vapor, solid, equilibria, melt, equilibria. Equation 6 will be dp by dt is equal to del fusion h by t fusion del v, where del fusion h is the latent heat of fusion, del f is melting point. The terms del v is equal to vt minus vs are different in volumes of melt and solid phase. Equation 7 can be dp by dt is equal to del fusion H by T F Vt minus Vs. For vaporization equilibrium, liquid changes into vapors. dP by dt is equal to del vapor H by Tb into Vv minus Vt, where del vapor H is the latent heat of vaporization, Tb is the boiling point, del V is equal to Vv minus Vt, the difference in volume of vapors and liquid phase. Now, since the volume of liquid is very small in comparison to gaseous phase, the term Vt in equation 8 can be simply be neglected. Or simplicity, dP by dt is equal to del vaporization H by Tvv. If the vapor acts as an ideal gas, PV is equal to RT, VV is equal to RT by P. The above equation can be written as dP by dt is equal to del vaporization H by RT square into P. 1 by P dP by dt is equal to del vaporization H by RT square, or d ln of P by dt is equal to del vaporization H by RT square. Above equation is popularly known as Clapeyron equation. One more popular forms of Clapeyron equation is the integrated form d ln of P is equal to del vaporization H by RT square dt. In the temperature change from T1 to T2, pressures is varied from P1 to P2. Del ln of P is equal to del vaporization H by RT square into dt. Ln of P2 by P1 is equal to del vaporization RH into 1 by T square dt. Ln of P2 by P1 is equal to del vaporization H by R into T1 by 1 by T1 minus 1 by T2. After converting the common logarithm, we get 2.303 log P2 by P1 is equal to del vaporization H by R into 1 by T1 minus 1 by T2. Log P2 by P1 is equal to del vaporization H by 2.303 R into 1 by T1 minus 1 by T2. This is integrated form of Clapeyron equation. Application of Clapeyron equation. First, for transition between a gas and a condensed phase, liquid or solid, Clapeyron equation can be given as ln of P is equal to minus L by R into 1 by T plus C. C represent a constant, L represent a specific latent heat for a liquid-gas transition. The boiling point of a liquid at any temperature can be determined if the boiling point of a particular temperature and latent heat of vaporization of the same are known. It is used to check if a phase transition will occur via comparisons and expansion in solid melt equilibrium. dP by dt is equal to del fusion H by Tf del T. V. Sign of dP by dt can be positive or negative for expansion and compression respectively. The latent heat of vaporization and vapor pressure of a liquid at particular temperature are known. The vapor pressure of same liquid at any other temperatures can be known. Law of mass action. According to law of mass action, the rate of chemical reaction is directly proportional to product of activities, or simply the active mass of the reactants, each term raised to its stoichiometric coefficient. Consider a reaction in which two reactants A and B react to form the product A plus BB is equal to change into CC plus DD. Then the law of mass action says that rate of the above conversions should be rate directly proportional to A to the power AB to the power B. Rate is equal to K into A to the power AB to the power B. K is the constant of proportionality and is typically labeled as rate constant of reaction. However, the actual rate of reaction may be or may not be equal to what is suggested by law of mass action, because actual rate law may have the power raised to active mass different from their stoichiometric coefficient. The actual rate law for the reactions given by equation A. Rate directly proportional to A alpha B beta. Rate is equal to K A alpha B beta. Comparing equation B and C, the law of mass action actually rate law will give the same result when A is equal to alpha and B is equal to beta. Different result observed when these are not equal. Thermodynamic derivation of law of mass action. To derive the law of mass action thermodynamically, general form of typical reversible reaction under equilibrium condition in which reactant and products are ideal gas A plus BB CC plus DD. As we know that the total free energy of a reactant GR can be GR is equal to A mu A plus B mu B, where mu and mu B are chemical potential of reactant A and B. Then total energy of the product GP is equal to C mu C plus D mu D. The temperature, pressure kept constants of free energy change of whole reaction can be obtained by substituting equations first, second and third. Del G reaction is equal to GP minus GR. Del G of reaction is equal to C mu C plus D mu D minus A mu A plus B mu B. Free energy change at equilibrium is 0. Equation fourth. C mu C plus D mu D minus A mu A plus B mu B is equal to 0. Now recall the expression of chemical potential of ith species in gas phase. Mu I is equal to mu I plus RT ln of Pi, where Pi and mu I are partial pressure and standard chemical potential of ith species. Now using equation 6 in fifth, we get C mu naught C plus RT ln of PC plus D mu naught D plus RT ln of PD minus A into mu A plus RT ln of PA plus B into mu naught B plus RT ln of PB is equal to 0. C mu naught C plus RT ln of PC C plus D mu D plus RT ln of P dd minus A mu naught A minus RT ln of PA minus B mu naught B minus RT ln of PB is equal to 0. RT ln of PC plus RT ln of PD minus RT ln of PA minus RT ln of PB is equal to minus C mu naught C minus D mu naught C plus A mu naught A plus B mu naught B. RT ln of PC PD by PA PB is equal to minus G naught P minus G naught R. RT ln of PC PD by PA PB is equal to minus del G naught reaction. Del G reaction is standard free energy. Change of reaction can be simply abbreviated as del G naught. Only equation 8 will be ln of PC PD by PA PB is equal to minus del G by RT. PC PD by PA PB is equal to e to the power minus del G naught by RT. Now because of del G is a function of temperature, only R is constant quantity, the right hand side can be put equal to another constant. E to the power minus del G naught by RT is equal to Kp from equation 9th and 10th. Kp is equal to PCPD by PAPB if the chemical potential of reactant and products are in mole fraction. Mu I is equal to mu I plus RT ln of xi. Equation second will be Kx is equal to Kxc, Kxt, Kxa, Kxa, Xb. Similarly, if chemical potential of reactants and products are in molar concentration, mu I is equal to mu I plus RT ln of Ci. Equation second will be Kc is equal to C to the power C D to the power D by A to the power A and B to the power B. This is popular form of law of mass action. Eutectic system calculation of eutectic point. General phase diagram for eutectic system. Complete phase diagram concept. Curve OX and SQ same as the phase diagram. Eutectic points area of ODQ and SQE in addition to enclosed area ODQ and SQE. There are also areas above OQS line and below DQS line as well. Area above OQS, it is obvious from the phase diagram that the area enclosed above the line QOS only has a liquid phase, which means f dash is equal to 2 minus 1 plus 1 is equal to 2 degree of freedom means that we can change the temperature whereas composition without disturbing completely melt state as long as temperature composition coordinates lie above the line OQS. Area below DQE. It is also obvious from the phase diagram that area lying below the line DQE has two solid phase. F dash is equal to 1. The only 1 degree of freedom means that we can change the temperature without disturbing the state of system. This curve DQ is also called solid is because they separate the fields of all solid from that of the liquid solid crystal. Area enclosed by ODQ. It is also obvious from the phase diagram that area enclosed by ODQ line has solid A plus liquid phase. F dash is equal to 1. Area enclosed by SQE. It is area enclosed by SQE lines has solid B plus liquid phase. F dash is equal to 1. Calculation of eutectic points. During equilibrium melting or crystallization in a closed system, the initial composition of system will be identical to final composition of system. Now consider the composition of liquid mixture in which compounds A is 80% and while B is 20%. It follows from above mentioned rule that after crystallization we must get the same composition 80% solid A and 20% B. Above temperature T, the composition X lies in field of all liquids and therefore will exist as liquid completely. When the temperature reduced to T1, the crystal forms of A will be initiated. The further lowering of temperature will make more crystal of A form. All this will result in a continuous change of composition of liquid mixture which is becoming more and more enriched in B. So as the temperature is lower T1 to T2, the composition of liquid will change from position X to point Y. Further lowering of temperature from T2 to T3 and then eutectic temperatures will change the composition from Y to Z. and then to C. As near point Q, the liquid will be rich in compound B relative to initial composition, and crystallization of compound B will also start at point Q. All the three phases coexist at Q. Even at infinitesimal decrease in temperature will disrupt the eutectic points, and liquid B will also start converting into solid phase. This will make the system move from point Q to Q dash, getting exactly the same composition, 80% solid A plus 20% B. Calculation of eutectic points. If composition of liquid mixture in which compound A is 80% while B is 20%, follow that after crystallizations we must get the same composition, 80% solid A, 20% B. If the system allowed to cool down and the temperature are plotted against time, we will get cooling curves above point A. The system is completely liquid, it will be cooled down very rapidly. The crystallization of compounds A will start realizing a large amount of heat, and rate of cooling will slow until point Q is reached. Since the system is getting solidified at eutectic point, it is moving from Q to Q dash. The temperature remains constant during this conversion. After point Q dash, both compounds will coexist in solids. The only difference will be that compounds B will separate out first up to point Q, and then solidifications of compound A will start. System forming solid compounds AXBY with congruent and incongruent melting points. System forming solid compound AXBY with congruent melting points. In this system, solid compounds melt sharply at temperature T with the same composition as the initial. These compounds are said to be possess a congruent melting point with phase diagram as. Consider two components A and B which also follow a chemical compounds AB by reacting with each other. Therefore, in complete solid state, there will be three phases named ABC solid. There should also be three freezing point curves OP, PQ, RS. In addition to the liquidus, there will be two solidus CE and DE. Curve OP and RS. The point OS represent the freezing point, the pure compounds A and B. When the compound AB is added to components A, its freezing point decreases regularly along OP. When the components AB is added to B, its freezing point decreases along SR. We can say that curve OP and SR represent the temperature condition at which solid A and B are in equilibrium with the liquid mixture. There are only two phases involved. Both are condensed in nature. After putting C is equal to 2, P is equal to 2 in equation, F is equal to C minus 1 plus 1. F dash is equal to 1, which means that system is univariant. If we define a particular composition of A and AB, the freezing point of mixture is completely fixed. Curve PQR. When compound A is increased in completely AB, its freezing point of decreasing regularly along QP. When component B is added to compound AB, its freezing point decreases regularly along Q, or F dash is equal to 1. It is also worthy to mention that at point Q also represent the congruent melting point of compound AB. Because liquid and solid phase have the same composition, the congruent melting point of compounds AB may lie above or below the congruent melting point of component AB. Eutectic points P and R. In order to explain the liquid phase can have two different composition equilibria with solid phase X and X dash. The curves P, Q, R is divided into two parts by vertical lines Q, Q dash. This makes the concepts very simple, as left and right parts can be treated as simply eutectic system. The right half of diagram is eutectic system with component B and AB, where left hand side is eutectic points with component A and AB. The eutectic temperature and composition for the left hand side portion are given by point P. Eutectic temperature and compositions from right hand portions are given by point R. System forming solid compound AXBY with incongruent melting point. These types of system, the components react to form a compound which is not stable up to its melting point. When heated, decomposition starts before the melting point is reached, and a new solid phase, a solution or melt with a different composition from original solid formed. C1 to C2 melts or solution, where C1 is compound formed by reaction between participating component, whereas C2 represents the compound formed as a result of decomposition of C1 below its fusion temperature. Consider two components A and B which also forms a chemical compound AB2 by reacting with each other. The cooling of all mixture composition is carried out in open vessels so that pressure remains constant. Plot of freezing point versus composition is obtained the following points. Point O, S, Q are the point O and S represent freezing point, the pure component A and B. The point Q is quite strange because it represents transition temperature where compound A B2 decompose into compound B. It does not decompose at this temperature. Congruent melting point would be R. Point R represent the hypothetical congruent melting point of compound AB2. Curve P, O, S, Q and QP. When the compound B is added to components A, its freezing point decreases regularly along OP. In other words, OP is fusion cause of compound A along which solid A is equilibrium with melt and solution. The line ISQ is fusion curve of compound B along which equilibrium with melts. QP is fusion curve of compound B AB2 along solid AB2 is in equilibrium with melt solution. When liquid mixture with composition X is allowed to cool down, it will do some by keeping its composition the same until point 1 is reached, where compound A will just start to separate out as solid. F dash is equal to C minus B plus 1. F dash is equal to 0. Which means there will be no degree of freedom at point P. If the liquid mixture with composition Y is allowed to cool down, it will do by keeping its composition the same until point 2. Raised whether compounds B just start to separate out as solid. Solid B plus solution convert into solid AB2. Therefore, formation of compound AB2 will be started, and since three phases coexist at this point, the point Q also becomes invariant and point Q is called pretectic point. Phase diagram and thermodynamic treatments of solid solution. In this type of systems, components are completely miscible with each other in solid phase and completely homogeneous solid solution are produced. General thermodynamic treatment of solid and solution. It includes the shift in solvent freezing points during the crystallization and nature of cooling curve, as well the shifting of solvents freezing point during crystallization. The thermodynamic expressions for the shift of solvent freezing point when the solid begins to solidify during cooling can be obtained by assuming the solid solution as an ideal solution. The chemical potential of ith constituent mu I can be given. Mu I is equal to mu I star plus R and ln of xi. Xi represents fractional composition of constituent, whereas mu I is the chemical potential of pure solid. Mu1 solid is equal to mu1 liquid. Consider both as ideal, as we can write above equation mu1 star s plus RT ln of x1s is equal to mu1 liquid plus RT ln of x1L. After rearranging, RT ln of x1s minus RT ln of x1 liquid is equal to mu1 star L minus mu1 star S. RT ln of x1s minus ln of x1L is equal to mu1 star L minus mu1 star S. RT ln of x1s by x1 liquid is equal to mu1 star liquid minus mu1 star solid by T. Mu1 liquid minus mu1 solid represent the molar freezing energy of fusion for pure solvents at P pressures and temperature T. R ln of x1 solid by x1 liquid is equal to del fusion mu1 star by T. Now putting values of molar free energy of fusions in above equation, we get R ln of x1s by x1L is equal to del fusion H dash 1 molar minus kT del fusions S1 molar by T R ln of x1 solid by x1 liquid is equal to del fusion H by T minus del fusion S. Recalling the entropy of the fusion for the pure solvent at temperature T1, del fusion S is equal to del fusion H by T1. Using above result in equation second, we get R ln of x1s by x1L is equal to del fusion H by T minus del fusion H by T1. R ln of x1s by x1T L is equal to del F fusion H into 1 by T minus 1 by T star. R ln of x1 solid by x1 liquid is equal to del fusion H into T1 minus T by T into T1. After putting T minus T1 is equal to del Tf. R ln of x1s by x1L is equal to del fusion H into minus del Tf T into T1. If the solution is very dilute, melting point T1 will be quite closer to temperature T, so T into T1 can be replaced by T1 square. So equation takes forms R into ln of x1s minus ln x1l is equal to del fusion H into minus del Tf by T1 square. For dilute solution we have ln x1s minus ln1 minus kx2s corresponding minus x2s. ln of x1 liquid is equal to ln of 1 minus x2l corresponding to minus x square l. Using equation A and B in equation fifth, R into minus x2 s plus x2l is equal to del f fusion H into del Tf by T1 square minus del Tf is equal to R T1 by del fusion H into x2 into 1 minus x2 by s into x2 by L. Recalling expression of molality X2L is equal to N2 by N1 plus N2. N2 of liquid by N1 of liquid is equal to N2 into M1. M1 by M1 is equal to N2 by M1 into M1. Using above result in equation 6, we have Tf is equal to RT1 by M1 by del fusion H m into 1 minus x2 by x2 of liquid. Del F fusion is equal to TFM into 1 minus K, where K is the distribution coefficient given by x2 by x2. The values of del TF can be negative, positive depending on magnitude of K. When del TF is negative, magnitude of del TF will be negative if the K is less than 1, which means T less than T1 star. When del TF is positive, the magnitude of del TF is positive if K is larger than 1, which means T larger than T star. The nature of cooling curve of solid solution as the two components are completely miscible, the maximum number of phases which can be coexist is only 2. Solid solution plus liquid F dash is equal to C minus P plus 1. After putting C is equal to 2 and P is equal to 2, F dash is equal to 1, which means degree of freedom is 1. Univalent system, only one variable is needed to